Welcome, this is EGME-331 Solid Mechanics. In this video, we are going to review torsion. Before we talk about torsion, we need to understand what's torque. So torque is a moment that twists a cylindrical object. So we have seen axial loads that acts along an axis in a straight line. Unlike the axial loads, the torsion or the torque produces stress across the cross section. So this is more like a shear stress as opposed to axial stresses or normal stresses. As we can see in the figure here, torque mostly acts on circular cross-sectional objects or cylindrical rods or shafts. So what the torque does is it twists the object along the axis of the rod while the cross-section remains circular. So torsion is nothing but the twisting of the object when a torque is applied. So within a material's elastic range, you can see this figure here, a shear stress is distributed along the radius of the shaft, and that starts from 0 at the center of the shaft all the way to the maximum at the outer edge of the shaft. So it is the torque that results in a torsion because it causes shear stress on the cross-sectional area of the object. Now if you compare torque versus moment, they are similar looking terms, but torque causes a change in angular momentum. That means it causes a twisting, whereas a moment is again a force which is applied at a distance, but it does not cause change in angular momentum, or it does not rotate the body when it is applied, whereas torque does cause the body to rotate about its axis. Here is the equation to determine torsion. What we see here is torsion is expressed in terms of the shear stress. In this equation, T would be the applied torque and R is the distance along the radius of the shaft. As we have seen here, depending on the location, center to the edge, the intensity changes. And J here is the polar moment of inertia. A little bit more about the polar moment of inertia. It is a function of the geometry and it does not depend on the material with which the shaft or the rod is made of. So the polar moment of inertia for a cylindrical rod is shown in this equation right here. J is equal to pi over 2 r per 4, where r is the radius of the cylinder.